Okay, good morning, everybody. Today's lesson is on the idea of friction. And friction is a topic that everybody is used to seeing. It is natural. It's around us. Um, it really governs everything that happens. And without friction, we wouldn't be able to do a lot of the stuff that we actually do, right? For instance, we wouldn't be able to walk without friction. The friction between the ground and our shoes is what enables us to walk. Um, for us, we have to understand the nature of friction. We have to understand how it works. And then, in addition, we have to figure out the mathematics of friction based just as another force, right? So today we'll focus on three main things. The three main things that we're going to be talking about is that friction is a force that opposes motion, number one. All right, number two, there's two types of friction that we're going to focus on throughout the course of the year. That's the idea of static friction and kinetic friction. And then finally, the two things that determine how big or what the magnitude of the friction force is are the size of the normal force acting on the object and the types of surfaces in contact with each other. All right, so let's start with this idea. All right, so friction is a force that opposes motion, right? Or it's a force that opposes desired motion. So we can have friction if there is no motion. Um, Now, the easiest part about friction that we've that's come to be viewed in your normal everyday life is the idea of friction when an object is moving. All right, so that's going to be the easy part for us. Perhaps a more difficult part will be the idea of friction when an object is not moving. All right, so friction is a force that opposes motion or the desire to have motion. So when we draw a force diagram with respect to friction, friction is always opposing motion. So if we're talking about this box, right, and the box moves in this direction, then friction is going to point in that direction. If the box is moving in this direction, then friction is going to point in that direction. And that's relatively straightforward and relatively simple. Obviously, it gets a little bit more complicated as we progress, and it's going to get more complicated right away when we talk about the two different types of friction. So we have two different types of friction, this force that opposes motion or desired motion. All right, and those two types are static and kinetic. And if you just think about those words, it makes things a little bit easier, right? Static means stationary, and kinetic means moving. The kinetic part is the easy part. So if I take this box and I slide this box along the table, then this box is moving. It's sliding across the table. It encounters friction between the box and the table. All right, because of the nature of that sliding motion. So if we think about that motion of the box here, as this thing slides across the table, let's analyze the forces that are acting on the box. So let's draw this box, right? And what are the forces acting on the box? Well, if we just look at the box as is right here vertically, we know that we have the weight force going down, and we have the normal force, F sub n, the table is pushing upwards. Well, if I push this box in this direction, if I push the box in that direction, then I am exerting some force F in that direction. Well, if the box is moving in this direction, the movement goes in that direction. Friction's job is to oppose motion. That is a friction force that would go in that direction. Now, it's super important for us to remember and understand here that the friction force is opposing motion. It's not opposing this force. Friction opposes motion. Oftentimes we'll end up in situations where there's a push force in one direction and a friction force in the other direction, because it's this force that causes motion for the object. But there are situations where the object is moving in one direction and somebody is pushing in the opposite direction. And therefore, the idea of friction opposing motion will come into play. Now, this idea of this friction force here, if this box is sliding across the table, then this friction force would be what referred to as kinetic friction. The force of kinetic friction opposes sliding motion. So that's relatively simple, right? And we're used to that, right? We have to overcome this idea of friction when we push objects. If there were no friction, if you're pushing something along a slippery surface, and we're going to talk about that when it comes down into this area here. But if you're pushing something across a surface, you encounter frictions. Friction's job is to oppose your motion. Oppose the motion of the object that you are pushing. All right. Now, static friction is a little bit more difficult. The term static means stationary. So this box right here, if we think about it as a stationary or static object, this is where the difficulty arises. All right. So friction is a force that opposes motion. Let's add to that, right? Or opposes desired motion. Now this is where Newton's laws kicks in, right? So here's this box. Here's this speaker right here. And if I draw a force diagram of this box with a speaker in it, if I draw that force diagram right now, we have weight going down and we have the normal force F sub n pushing up. Now, if we think about Newton's law of inertia, this box is at rest. Its desire is to stay at rest. So if the box desires to stay at rest, then it has no motion. So there's no friction that's opposing its motion because it's not moving. In addition, it has no desire for motion because what does an object at rest want to do? An object at rest wants to stay at rest. So this box right here as it sits on the table, and if you're looking at your desk and your computer is sitting on your desk and your notebook is next to it and it's sitting on the desk, and you have something to drink and it's sitting on the desk, those three things and everything else that's sitting on your desk or the table that you are at have no desire for motion. They are at rest. They want to stay at rest. So therefore, they have no desired motion. So there's no need for friction to act because there's no motion and there's no desire of motion. However, the second I push on this box, I am now pushing on this box, which means there is a friction or there is a force that acts in that direction. Well, if I look at this force diagram, if I am pushing like this, that can't possibly be the force diagram that causes this motion or lack thereof. Because if we look at this diagram, this object would have to be accelerating because as this diagram lies, there is no force that is balancing out this F. So these forces horizontally are unbalanced. That would cause an acceleration for this box. As you can see, there is no acceleration for the box. So if this box is not accelerating, then there must be forces that balance things off in the horizontal plane. So there must be a force. What is that force? It's the force that opposes desired motion. Why? Because right now the box has no desire for motion. It's at rest. It wants to stay at rest. Well, as soon as I push it, if this were the only force acting on it, then it would desire to accelerate. It is not accelerating, so there must be some other force. Well, that other force is the force of friction. In this particular case, it's the force of static friction. How come? Well, because the box isn't moving, right? This box is not moving. It's static. Static friction is the friction force that opposes desired motion. Kinetic friction is the friction force that opposes sliding motion. Now I got to put a charger on my computer. It's running out of battery here, so let me get this thing charged and we'll be ready to go. All right, so we got two types of friction. Sliding friction opposes this sliding motion. Static friction opposes desired motion while an object is still stationary. All right? Now, there's a major difference between these two things, static friction and kinetic friction. Obviously, one major difference is static friction acts when an object is stationary, and kinetic friction acts when an object is sliding or moving across a tabletop or a surface. The other big thing is that static friction is a variable force. In other words, its size can vary. It varies up to a particular limit, right? So there's a maximum value for static friction, but it's a changing value, or it can be a changing value. Here's what I'm talking about, right? So look at what we got going on right now. This speaker, when I push it like this, desires to move. Well, it's not moving, it's not accelerating. So there must be a static friction force. I'm going to call it F sub S, a static friction force that opposes this push force. This push force wants to accelerate the object that way. It's not accelerating, so therefore there must be a force that is balancing out. That force is the force of static friction. Now let's just think about this. And everybody's been through this situation in their lifetime. You're trying to push something across the table. You're trying to get it going. Well, you can't get it going just yet, so what do? You push harder. Well, if I push harder, then this force right here is getting bigger. Well, if this force got bigger and the static friction force stayed the same, we would have unbalanced forces. If I push on this a little bit and nothing happens, that's because the static friction is opposing that. If I increase my push and I push harder, if static friction didn't increase with that friction force or with that push force, then the object would accelerate to the right. But because I can push on this thing, oh, it doesn't move. Now I push a little harder, it still doesn't move. Well, what has to be happening to the static friction force? It has to be getting bigger to match this push force. And everybody's been through this, right? You push on something, it doesn't move. You push harder, it still doesn't move. You push even harder. Well, your force is getting bigger, and therefore the force of static friction also has to be getting bigger. But eventually, if you push, you finally get that thing moving. Well, if the box is moving, there's no more static friction. Instead, we now have sliding friction. So this idea of static friction, this is important for us. This is variable in size up to a limit. So there's a maximum amount of static friction that an object can have with a particular another object. Kinetic friction is not a variable amount of friction. This is a set specific amount. As this thing slides across the table, the amount of friction between these two surfaces is a set amount. The static friction is what is variable. Right now, there is no static friction because this has no desire to move. If I push it a little bit, now it's got a little bit of a desire to move, so I need a little bit of static friction to keep it stationary. If I push it a little bit harder, we need a little bit more static friction to keep that thing from moving. And so on and so forth until I finally reach that limit. So we've got a variable amount of static friction up to a limit, and we've got a set amount of kinetic friction. Now, what is it that determines the size of those two forces? And that's the last little bit here for our little introductory lesson that we have here for class. The magnitude or size of the friction force is determined by the magnitude of the normal force and the two types of surfaces in contact with each other. All right, now let's talk about the two types of surfaces in contact with each other. All right, well, that's kind of intuitive for us, right? If we have a slippery surface, we have less friction. If we have a surface that grips a lot, we have more friction. Try to walk on ice in the wintertime, and there's not that much friction. It's hard to do. Walk on a rubber mat, that's usually easy to do. So the two types of surfaces that are in contact determine how big a size of friction there are. Slippery surfaces, less friction. Sticky surfaces, more friction. All right. Now that's relatively simple, right? So like, how could I make this have less friction? Maybe I could spray some cooking oil on there, right? Or maybe I could put some grease on the table. Either way, the difference in the two surfaces, box is one surface, table is another surface, those two surfaces determine the size of the friction force. Now, we need a quantifier that dictates that. The quantifier that provides a number for the two types of surfaces in contact is called the coefficient of friction. The coefficient of friction is the quantifier for the types of surfaces in contact. The coefficient of friction is often called mu because it's represented by the Greek letter mu. What is it? It is the quantifier, I like to say, the quantifier of the two types of surfaces in contact. And we'll spend more time talking about that. But as an introduction, that's good enough for us. Now, the other thing that determines how big the friction force is the normal force acting on the object, right? And a lot of people will confuse this by saying it's the weight, right? So if we were in class and I were soliciting answers, it's relatively easy for us to come up with these two things that determine the magnitude of the force of friction. Usually they come up with just like that, right? The two types of surfaces, that's usually easy. And then usually people will say the weight of the object. And while the weight of the object is a factor, it's really only a factor in changing the normal force. All right, so let's think about this. Friction kind of tells us how much the two surfaces stick together. So here's the box and here's the table. Friction kind of tells us how much the two surfaces stick together. Well, if I have a heavier box, then definitely for sure, this weight would go up and therefore the normal force would go up. The weight being heavier certainly causes the box to stick to the table more. But in reality, it's the normal force that dictates how big the friction force is. Because think about it. How else could I get this box to stick to the table more? I could push down on the box. Well, if I pushed down on the box, the table and the box stick together more. Well, what would that look like on this force diagram, for instance? I'd be adding this other force. I'm going to call this F sub P. That's the force of me pushing downwards. Well, if I'm pushing downwards, then what has to happen to this normal force? This normal force has to get bigger. The weight hasn't changed, but I'm pushing down on the box. That would cause the table and the box to stick together more. That would mean there's more friction between the table and the box. How else could we make the table and the box stick together more? I could put some weights on top of here. Have I changed the weight of the box? I have not changed the weight of the box. So therefore, I haven't changed this force. But clearly, the box and the table would be sticking together more. How come? Well, I put two things up on top of there that are exerting a downward force. And if those two things on top of there exert a downward force, then the table has no choice but to exert a bigger upwards force. So our two things that determine the size of the friction force are the normal force. How much does the table push up, or the surface or whatever, and the two types of surfaces in contact. All right, now, where does that lead us? That leads us to a mathematical expression that we will utilize a lot. The friction force is equal to mu times the normal force. This is the mathematical representation of this thing right here. And that is our introductory lesson for friction.